So, okay, even here in the classroom, please. Hello again. Are there any questions related to that, what we discussed last week? Excuse me, here in the front, please be quiet. I can't understand here. Is there any way to calculate, or what is the question? Well, this is what you have to learn. And at the end, it's only one which you should know. It's sodium chloride. And the coordination number for that is 6 for both ions, for the positive charge and the negative charge. And we just discussed about other examples, yeah, which are in the AB type. We talked about the AB2 type. And here you should know, of course, there are existing other coordination numbers. Even the structure is totally different. But we do not have a look on them. Just to be aware, these ionic bonding leads to different types of crystals. One example is the sodium chloride type. Here we have these tetrahedral surrounding of one of the ions, and the coordination number is 6 for both. That's all. And just knowing, of course, there are many other types, and they are distinguished related to their type. Is it AB or AB2? And to their coordination numbers. And they, yeah, you should know they are existing, and there are existing quite a lot. You don't have to know them. Okay. Other questions? Okay. So, well, what we stopped with last week was talking about the solvatation, you know. Solvatation was that what we discussed at the end of our lecture. We had the hydrogen bridges, which is a van der Waals type of bond. And we talked about the solvatation, which is another aspect, and water structure is here helping to solve ions. So salts, as example, our common salt, sodium chloride, is stabilized in water. On the one hand side, the sodium plus ions are stabilized, and on the other side, the chloride minus ions are stabilized due to the fact that we have a dipolic character in our water molecules. And this is the case because we have different electronegativities. So the oxygen has a higher electronegativity compared to the hydrogen. So the electrons in this chemical bond, which are built out of 2 electrons are more on the side of the oxygen, because oxygen has more power to try to place the electrons nearby oxygen, and therefore we have a partially negative charge on the oxygen and a partially positive charge at the hydrogen. Important to have these type of dipole is additionally this angular structure of the molecule, because if that would be linear, it won't be a kind of dipole, because then we have the oxygen in the middle, and of course the negative partially charge will be in the middle, but it's not a dipole. It's not separated into directions. So we need even the angular structure and the electronegativity. And then we have here a negative partially charged part in the water molecule. And of course, plus minus is interacting. So the positive charged ions are stabilized as single ions solved in the water. And that is what we call solvatation. There was a question here? No? Okay. And vice versa, the same for the chloride. Here, of course, the positive part of the water molecule is oriented to the negative chloride ions and stabilizing these negative ions. And that's the reason for this high solubility of common salt in water. Always when we have a structure like an ionic structure, of course not all of them are as soluble as the sodium chloride, but yeah, we can explain in general the high solubility of such type of ions in water. Yeah. Later on, we will talk about the solubility product. And the solubility product, of course, is a value telling us how much of this salt we can solve in 1 liter of water. But here we are not talking about the gram. Later on, we will talk about how many mole. But it's not difficult to transfer gram in mole. We already know. Therefore, we need the atomic weight of the elements, and then we can transfer that in mole, or vice versa. And the solubility product we will explain later on. But this value gives us the number of how much of this sodium chloride we can solve in water. And for this type, it's very high. So we find 2 different values for the solubility. One is in gram per liter, and the solubility product is in mole per liter, or in mole square per liter square. We will explain that later on. Okay. So this is what we had to talk about, the ionic bond. Now we try to talk about the covalent bond. So today, I think it's the 25th of October. And now we start a new chapter. Well, the general chapter is chemical bonding. We talked about the ionic type now. And now the second one is the covalent bond. Well, therefore, we have to talk about something which you might already know. We come back to the electron configuration of our different elements. And then we try to explain what is a covalent bond. And therefore, we need the valence or the excited state. So when we talk, for example, let's talk about nitrogen, N. Nitrogen. Well, the electron configuration of nitrogen, we have 7 electrons because we have 7 protons. So 7 electrons have to be placed. Anyone who can help me? What is the electron configuration of nitrogen when we have to place 7 electrons? Please. Yeah, we did it a little bit different. We talked about the orbitals. In which orbitals do we have electrons when we are talking about the most stable position? The 1s is full, so 1s2, 2s2 full also. Ah, 2p3. So please look it up. That is the way how we are describing the electron configuration. We talk about the first orbital, which is the 1s. In the first main shell, we just have one orbital, which is the s. In the second, we already know we have s and p. And so we have the s full again. And in the p, here we have 3 different orbitals, px, py, pz. In each, 2 electrons can be placed, but we just need place for 3. In total, 7. If we are now trying to draw the energetic level of those 3 different energetic levels, well, what is it? When we have here in the y-axis the energy level without any value, just qualitatively, we start with the 1s. That's the most stable. And what we know, how to fill electrons, we need the opposite spin. 1, 2. So the 1s is full. This is the 1s orbital. The next one, 2s. It has a higher energetic level compared to the 1s. And it is filled as the next, again, 2 electrons. We know related to the rules we discussed, we need a set of 4 different quantum numbers. And here, the difference is the spin, because we are in the same orbital, but the spin is different. So now we're in the 2s. And now, is it a little bit higher in the energetic level compared to 2s. And we have 3 px, py, and pz. And how now do we have to fill it up with electrons? 3 in each orbital, 1 with the same spin. That is what we already learned. Now we're done. That's 2p. So we fill it up from the most stable position bottom up. And then we have to calculate how many electrons we need. And we fill it up related to the rules we know. So now, what do you think? How many partners a nitrogen atom can have when it tries to create a chemical bond to any kind of partner? 1. 3. Why 1? No, we have to fill it up, and therefore we need 3. So for the nitrogen, we will have at the end, when it's willing to go into any kind of chemical bond, 3 partners. Because we have a place for 3 electrons, and we need even 3 electrons if we want to create a kind of octet in the outer shell. Octet always means 8 electrons in the outer shell. This is the second one here in this case. So when we look to a nitrogen compound, which is ammonia, do you know the formula? NH3. NH3 is the formula for ammonia. And we even know now, we do not look to the first shell because that is full. We always look to the outer shell, and the outer shell is now the second one. And here we have 2s and 3 electrons in 2p. So when we'd like to draw the structure of ammonia, we have here the nitrogen, and the 2s electrons, they are already fine. So we try to symbolize it with a line, meaning this is a pair of electrons which are not included into any kind of bonding. These are the 2s electrons. And what we know, we have now 3 electrons from the 2p. 1, 2, 3. They are free for the creation of a bond to any partner. Now, our partner is hydrogen. What do we know about hydrogen? How many electrons? Only 1. So the hydrogen can contribute to that bond with 1 electron. Again, another one, and a third one. So we have here, coming from the hydrogen, 1 electron. And now we see we have now the chance to create a chemical bond between those elements. This is now symbolized as a line. Later on, we just will draw the line, not the dots. So we have a chemical bond to 3 partners. Can you see the geometric structure of this molecule? How will it look like in reality? Out? Yeah, maybe you mean the right thing, but you describe it a little bit not in the way I'd like to see or hear it. This is a pyramid, a pyramidal structure, because here, if you like to draw that not on the way we did, you have these triangle on the bottom. Here, the line behind, we can't see it. So you have a triangle. And we have here 1, 2, 3, 4 sides. So this is a pyramidal structure. On the top, we have the nitrogen. And in this triangle, in the plane, you have those 3 hydrogen. Can you see it? Okay. That's about nitrogen. Now let's have a look to carbon. Carbon is one of the most important elements in organics, in life. So when we try to do the same for carbon, now carbon, see, let's have a look to the periodic table once more. Carbon, how many electrons do we have to place? 6. Only 6 in total, no? So we have, talking about the electron configuration, 1s2 full, 2s2 full, and 2p, only 2 electrons now in the p orbital. Well, first of all, normally always the orbitals are full because they are more stable. They, from the energetic point of view, they are below the 2p. So we fill them up and they double up before we go into the p. Yeah, that is what I'd like to describe now in the next step. But the normal expectation when you look to a single carbon atom, then it looks like this. So if we are drawing the energetic level of those, again, we have here the 1s, we have here the 2s, and here the 2p. And now we fill them up with electrons, opposite spin, doubling up with opposite spin, but now only 2 electrons in the p orbital. In total, 6 electrons. So when you now try to think about how many partners are we expecting now when we try to build a chemical bond to any kind of partner, how many partners do you expect? F4 is what we will see later, but when you just see that, how many are you expecting? 2. We have only 2 electrons, which will be present to build up a bond to any partner because they are satisfied, they are satisfied. So nothing happens. That is what we would expect. Only 2, because here we can have a 1 and here we can have 1. And if we'd like to have more, those are in an energetically stable position. They won't participate in creating a new bond to any partner. But that is not the reality. The reality is we have 4 partners for the carbon. So the expectation would be 2 bonding partners. And the reality, the experiment shows 4 bonding partners. So this is what we'd like to explain in the next step. And that is what we now call excitation. So again, draw our energetic diagram of the orbitals. We have the 1s, we have the 2s, and the 2p. And well, the starting point is, as we already did, we have to place those 6 electrons in the outer shell. what happens now is we call it excitation. One electron of the 2s is jumping up in the pz orbital, and in the same step, the 2s and the 2p will equilibrate in the point of the energetic level. So after this excitation, we call it excitation, it looks like that. We have the energetic level diagram. We have the 1s is not touched. And now the new orbitals, we have 4 of them now, are on the same energetic level in between 2s and 2p. And in there, we have one of the electrons jumped up. So we have 4 in total in this new type of orbitals. And now we can say, and of course in the 1s, it's full. And now we can say, okay, now it looks like having the possibility to build a bond with 4 partners. So that happens because the energy profit, when it is building a bond to the 4 new partners, is higher than the need for the excitation. So bonding energy is higher than the needed energy for excitation. And that means now in the second period, please remember, we have periods and we have groups in the periodic table. We are now in the second period. First is just hydrogen and helium. Second, here we find carbon. In the second period, there are maximum 4 covalent bondings possible. So in the second period, maximum 4 covalent bonds possible. And when we are in the third period, what is now additionally, when we talk about the orbitals, what is new in the third period? We talk about the orbitals. What is new for the second period? And in the third? Yeah. Yeah. That is what we had already talked, where we already talked about now. We are here in the first period, we just have s orbitals. In the second period, we have s and p orbitals. In the third period, we have 3s, we have 3p, and we have 3d. But from the energetic level, 3d is above 4s. And that's why after 4s filling up with electrons, the 3d orbitals are filled, and then the 4p. Please remember that rule which we were drawing, how to fill up the orbitals from bottom up related to their energetic level. That's why we have the 3D not here, we have them here in the fourth period. That's the reason. Okay? So in the third period, we have all even d orbitals, and so there are quite a lot of different options for chemical bonding, not only 4. Here we can have more. So, of course, do not wonder if we have sometimes more than 4, then we are talking about elements which already have d orbitals. Well, to go on with this, we talk about these so-called overlapping of atomic orbitals. Overlapping. And maybe you heard about sigma. Let's talk about a sigma bond. On the example of hydrogen, you know, each hydrogen atom contributes with 1 electron, 1 and 1, and this is now creating a chemical bond between those 2 atoms. When we try to draw it, the overlapping s orbitals, then we know we have our proton in the middle of our atomic structure, and we have those orbitals which are looking like a ball this electron cloud, and we have two of them. And what we find is an overlapping area. And in this overlapping area, the probability to find those two electrons is the highest. So the statistical probability for the residence of the two electrons is exactly in the middle between those two nuclei. The statistical probability for the residence for the two electrons is exactly in the middle of the two nuclei. Do you already know what is characteristic for any type of sigma bond? What is the characteristic of sigma bonds? Sigma bonds, we can rotate on their common axis. If you try to rotate, you have two balls, these are the s orbitals. And when they are overlapping, you can rotate, nothing happens. The overlapping area will be stable. So sigma bonds are, from the point of rotation, symmetrical, rotationally symmetrical. And we have different types of sigma bonds. What we draw just now here above is the SS type sigma bond. Now here we have a common axis where the hydrogen atoms, for example, are located on with the two nuclei, and the s orbitals are overlapping. And we can rotate and nothing happens. And this is our x-axis. So they are on the same axis and we can rotate without any change in the bond. Do you have an idea which other types of sigma bonds we could have? Do you remember the geometrical form of the p orbitals? How are the p orbitals looking like? Yeah. So, but first, the question is, do you know, can you describe the structure of a p orbital? Mm-hmm. Yeah. This is this, we call it dumbbell ball look like, yes? And now we can have a structure where we have one, on the one side, we have an S, and let's talk about the px on the other side. And then we are on the same axis again, x-axis, and we have an s orbital, and we have a p orbital. So the s looks like above, same. And the p, as you already described, we have these dumbbell ball-like structure. And even here, we have an overlapping area. And when we rotate, nothing changes. When we now look to px and py, we have px and py. Can we have the same situation when we look to these two different orbitals? No, because we have an x direction, we have a y direction. Here we cannot create that overlapping area. What we can is between px and px, or py and py, or pz and pz. Then we have the same axis. Then it works. But px and py doesn't work, because then we don't have these overlapping area. So just as an example, px, py, no, but px, px could work. Because then, again, we look to the x-axis, x, and now we have 2 times the p orbitals in the x direction, and they are looking, as already mentioned, the dumbbell ball-like. And even here we have the overlapping area, and we can rotate, no problem. So sigma bonds are rotationally symmetrical. That works for all of these three. For px and py, when one is x direction, the other y direction, there is no option to overlap. The next step, what we have to discuss now, is the so-called hybridization we already started with. All this is necessary to understand the geometrical structure of molecules and what is possible and what's not possible. And what we have to discuss in the first point is the so-called sp3 hybridization. The sp3 hybridization. And that is what we already had. Here we have an s and we have p orbitals. We have one s orbital and we have 1, 2, 3 p orbitals. And that always we have at the beginning 4 orbitals. And when we do the hybridization, we have again 4 orbitals. But now we call them sp3 hybrid orbitals. They have the same energetic level, and we call them sp3 hybrid orbitals. So what's the number? We have 4 of them because 1 s and 3 p orbitals are involved. sp3 hybrid orbitals. Yeah, of course, they are looking a little bit different as just an s or just a p orbital. And we draw it in the example for a methane molecule. You know the structure, the formula for methane molecule? What's the formula? CH4. Now we already talked about, we have 4 partners possible now, and it's CH4. Do you even know the geometrical form of a methane molecule? Anyone? No? Anyone knowing the geometrical form of a methane molecule? We have our carbon, a tetrahedra. Yeah, we have the carbon in the middle of a tetrahedra. And on the edges of that tetrahedral structure, we have the hydrogen atoms. So the structure of those hybrid molecular orbitals, the sp3, is looking into the edges of a tetrahedra. So, well, what we know, of course, we have these s orbitals. I now symbolize it like this. The s orbitals from the hydrogen. That's what we already know. It's a ball. These are the s orbitals which can be contribute with 1 electron coming from the hydrogen. And the other 4 sp3 electrons, the orbitals are looking like that. We have here similar to that dumbbell ball, but now the opposite direction is small. And we have 4 of them looking into the edges of a regular tetrahedra. Can you imagine? Now we have 4 times that overlapping area here from the S and the sp3, the S and the sp3, the S and the sp3, the S and the sp3. So 4 times overlapping. Are they sigma or other type of bonds? Can we rotate here? We can. So it's in each case a sigma bond, and the structure in general is looking like a tetrahedra. Here, and here, and even here, we have these structure. If you can imagine, this is our tetrahedral structure. In the middle of the tetrahedra, we have the carbon, those sp3 hybrid orbitals looking into the edges. And from the hydrogen, there is nothing to change. It's just a normal 1s orbital. So we have 4 equivalent sp3 orbitals. Look into the edges of a regular tetrahedron. And they are built out of 1s and 3p orbitals. I don't use, I write 1s and 3 p orbitals. It must not be the 1s and the 3p. It is just the number out of 1 and out of 3 of the p orbitals. One s and 3 p orbitals. That's why we call it sp3. We need one s orbital and we need 3 different p orbitals. In total, they build 4 new, and we call them sp3. And they look like that. So that's sp3. What do we expect when we have sp3? What could be another type of hybrid orbitals? The sp3 is built out of 1s orbital and 3p orbitals. So looking like that. Or in a geometrical form, looking like that. Now we have just, again, 1s and only 2 p orbitals. And that's the sp2 hybridization. Now we just need one s orbital and 2 p orbitals. When we start, we have our coordinate system. With all the 3 dimensions. X, Y, and Z. The s orbital normally is located around the nucleus, a ball-like. That is the s orbital. And we have 2 p orbitals. When we just talk about the structure in the carbon atom, then let's talk about the px orbital and the py orbital. This is our starting point. When we just look to carbon, we have 2 electrons in the 2s orbital, and we have 2 electrons in the px and py, each one. This is the 2 p orbitals. And we show it on the example px and py. In this case, the so-called hybridization leads to another structure. Now, again, our coordinate system x direction, y direction, z direction. And now the new type of orbital looks like this. We have again this dumbbell ball, but now we have the structure which looks like this. Oh, sorry, wrong. No, I mixed it up. Again, drawing our coordinate system. I do it above, sorry. So X, Y, Z, and these are directly on the axis. And on the x-axis here, and they are building a trigonal planar structure. So it's looking like this. And the angle here in between is exactly 120 degrees. That is 3 times means 360, which is a circle. Now we have 3 equivalent sp2 hybrid orbitals. S1 coming from S, 2 from the P, so sp2, and these are the 3 equivalent sp2. Hybrid orbitals. And they are looking into the edge of a triangle. So the structure is trigonal planar. Now we are in one plane and we have it in a triangle. Before we had it in a tetrahedral structure. Here we had the tetrahedral structure of those 4 hybrid orbitals, sp3 type. And for the sp2 type, we have a trigonal planar structure. And last but not least, the last one is the sp type. Now, one s orbital and one p orbital is involved. And now again, we just look to one axis, the x-axis. When we start with the atomic structure, we focus here on our nucleus, and we have these s orbital, and only one p orbital is involved. And the hybridization now leads to two different geometrics, but with the same energetic level. The hybridization now we have at the end looking to the x-axis. And here we have our nucleus. Sorry. Then when we have one sp orbital looking like this and the other one just in the opposite direction. So we have two equivalent sp orbitals. Can you please open the one of the windows or more here? Maybe just off. Yeah. Need a little bit fresh air. Well, why are we talking about that? Because now we'd like to talk about, besides the sigma bonds, we have another type of bonds. Do you know what they are called? How they are called? The pi bonds. And what's the difference between the sigma and the pi bonds? Now we talked about the rotationally symmetry of sigma. Do we have that for pi as well? No. That's the difference. Pi, we cannot rotate. The pi bonds are fixed. If you look to that dumbbell ball structure in the px, and you have a second atom, again with the px, and now you try to overlap them. That's possible. Here and here they are overlapping. Now I rotate, so the lower overlapping area is lost. We cannot rotate. This type of bond is fixing the rotation of the atoms or the structures in the molecules. When we have a pi bond, we cannot rotate. When we have sigma bonds, we can rotate as much as we want. The bond is not lost. But for pi, just try to imagine when I rotate, the rotation, the overlapping area is lost. And that's the difference. So let's talk about the pi bonds now. Again, come back to our nitrogen. We will not find nitrogen as a single atom. The gas nitrogen is a two-atomic gas, N2. And from the from the above done thoughts, we have 5 electrons from each nitrogen. One is from the 1s satisfied, and the 2s and 2p. The 2s satisfied, we are just looking to the outer shell, but the 2p, we have single electrons. So for one nitrogen, this is the 2s, and we have 3 single electrons, 1, 2, 3. And from the second one, we have the same. E2 satisfied, and 1, 2, 3. So nitrogen can build a triple bond to the other one. No, because we have these atomic structure, 1s2, 2s2, and 2p3. In total, in the outer shell, 5 electrons, 1, 2, 3, 4, 5. When we look to this structure, we have the, well, let's draw it in the energetic levels. We have the 1s. We have the 2s. And we have the 2p. One S2, 2s2, and 2p3. That means now we have full. We have full, and we have 3 electrons in the 2p level. So we can create 3 bonds. And that is what we see. We have 3 bonds, 1, 2, 3. But now, how is it looking like when we try to draw these bond structures, knowing now these different sp, sp2, or sp3 hybrid orbitals, which are always built when we talk about molecules? We are not talking about atoms now, we talk about a molecule, N2. And when we try to draw this, it needs a little competence in geometric structures. So we have the x-axis, which is our main axis. And what we have is 2 atoms now. So we have here a y-axis, and we have here a y-axis. And additionally, we know the third axis in the 3-dimensional space, that is our z-axis. So this is y, this is y, this is now z and z. And this is the nucleus of the first nitrogen, and this is the nucleus of the second nitrogen atom. Now we have the px orbital. So the px we do not touch. So we have a px orbital from the left nitrogen atom, and we have a px orbital from the right nitrogen atom. What is built when we talk about those px orbitals? We have an overlapping area. Is it a sigma or is it a pi? This only looking to that. Is that a sigma or is it a pi bond? It is a sigma, of course. We can rotate. It's on the same axis. No problem. Now, let's talk about the next. Now, we have here, next, we talk about the py. And we talk about the py. I did not draw it as close as needed to see the overlapping area, but you might imagine we can overlap here and we can overlap here. So this is now py. The other one was px. Here we can overlap and rotate. But in py, we are not able to do that. The py overlapping area here is a pi bond. We cannot rotate. Last but not least, we have the third one, which is the pz. In the z direction, it looks confusing at the end. But when we try to imagine as well, the pz is the same as py. Here pz and here pz. Even in the pz, it's just the third dimension. The balls are overlapping, but not in that manner. In that manner, and when we rotate, we lose the overlapping area. So in the py and in the pz direction, we have pi bonds in py and pz direction. In the px direction, here, this one, px, that's a sigma bond. So one of those three bonds is a sigma. Two of them are pi bonds. So at the end, it doesn't help. The sigma, of course, we can rotate, but the other two are blocking the rotation in the same, it's in between the two atoms, so we cannot rotate. So the nitrogen has one sigma bond and two pi bonds. One sigma and two pi bonds. When we'd like to draw it once more, we have N and N, the two which are not involved. And we have one sigma, the red one, and the two different pi bonds from py and pz. So we have three, a triple bond, two pi, and one sigma. This is pi, and this is sigma. Pi bonds are not rotationally symmetrical. They are not rotationally symmetrical. That means if we have one or two pi bonds in between two atoms, we cannot rotate that structure. Well, let's talk about a real example. I'd like to ask you maybe later on, or not maybe, we will later on talk about it, but maybe you already know it. The example is ethene. Ethene, not ethane. We are talking about ethene. Do you know the formula of ethene molecule? You know, ethane, methane we already had, CH4. And the ethane, what's ethane? Again, please. C2H, how many H? For the
H4.
ethene. For the ethane, it's yeah, C2H6. So ethene is, you're right, C2H4. And do you even know the structure when we now try to draw the structure not related to the bonds? Now we have the structure that we have 2 carbon atoms and 4 hydrogen, 1, 2, 3, 4. And in between we have a double bond, CH4. Please always think on that. Carbon, in any case, needs 4 partners. Now we have 1, 2, so this is the same partner, but we have a double bond, 3, 4. If you have to draw a structure of any carbon molecule, always think on that. 4 bonds are needed. It could be another carbon or any other atom, but we always need 4. So 1, 2, 3, 4, because we have those 4 electrons in the outer shell. So one of these is a sigma bond, and the other one is a pi bond. So we are not allowed to rotate. We cannot rotate. Try to draw it with our geometrical form of the orbitals. Again, we have here the x-axis, and we have here 1 carbon atom, and we have here the other carbon atom. And now we have the so-called sp2 hybridization in this case. Do you remember how the sp2 type orbitals are looking like? We just talked about a few minutes before. The sp2. So we need 3 orbitals. 1 is from S and 2 from P, and then they are hybridizating. And how is the hybrid orbital looking like? Yeah, we have these looking into a trigonal planar structure. So we have these sp2 hybrid orbitals. So in the x-axis, and here again in the x-axis. So we have 2 of them from each atom. And in the trigonal planar direction, so we have here 1, and we have here 1, and we have again that is not the case, sorry, it's just a small one, and we have here 1, and we have here 1. So we have the overlapping area here. I will draw it once more because maybe it's confusing, sorry. Again, x-axis, we have 1 carbon, we have the second carbon, and we have these trigonal planar structures. So we have the sp2 type, and they are looking more like that, not the big one in the other direction, and here, and here, and here, and here. So here, this is our sp2 hybrid orbitals. They are looking into the edges of a triangle. Here we have the hydrogen, here we have the hydrogen, here we have the hydrogen, and here we have the hydrogen. From the hydrogen, we know it's just an s orbital. And we have here the overlapping area. These are all sigma bonds. And even this one here from the hybrid orbital, that is a sigma, because we can rotate. But there is remaining now a py orbital from the carbon on the left side. And from the right side. And here we have an additional overlapping from the py, and this is a pi bond. This now is fixing the rotation. We are not allowed to rotate. Here with just the sp2 type, this is symmetrical. We can rotate. But the pi now, out of this plane, we are not allowed to rotate. And this is important before we have the break to have a look on the importance of that structure. Takes 3-4 minutes more. We'd like to talk about the 1,2 dichloroethene. So the name is 1,2 dichloroethene. Now I'm saying we have two different molecules possible with that name. Can you imagine what? Yeah, but you have to describe it a little bit more detailed. Where do we have the chloratoms? When this is the normal ethene. And we just say that's molecule 1 or atom 1, 2, 1, 2. So we have two carbons, 1 and 2. And we say 1,2 dichloro. What does it mean for the chloratoms? Oh, instead of the hydrogen, what is the formula of that? The dichloroethene, now the formula is C2H2Cl2. It's an ethene. We have a pi bond and a sigma bond because the name ethene, E-N-E, always says now we have a double bond between the carbon. So that does not change. So we have here C atom, double bond, C atom. Now, please tell me, where do we have the chloratoms when we talk about 1,2 dichloro? I will help you. The other option is the 1,1 dichloro. What is the difference between the 1,2 dichloro and the 1,1 dichloro? Yeah. So this one is easy. The 1,1 dichloro. The structure is the following. We have the chloro on the same carbon atom, 1,1 dichloroethene. The sum formula is again C2H2Cl2. It's the same as we have it here, but now we say 1,1 dichloroethene. That is our second carbon atom, and we count from one side. And we say this atom which has another than hydrogen is the 1. So we have the 1,1. The 2,2 might be the same, but then we just count from the right side. Then it's the 1,1 again. And what's now for the 1,2 dichloro? Yeah. And now I tell you we have two different options to place the two chloro atoms on the atoms C1 and C2. The one is this one. We have the Cl here, and we have the Cl here. And the other one is we have the Cl here and the Cl here. This is a difference. Why is it a difference? We are not allowed to rotate. So here they are on the same side, and here they are on the opposite side. We are not allowed to rotate. So these are two different molecules. Do you know the name of this? Anyone? We call it cis and trans. This one is the cis 1,2 dichloroethene. And this one is the trans 1,2 dichloroethene. Because here we have the chlor atoms on the opposite sides. And here we have them on the same side. And we are not allowed to rotate. Cis and trans are different molecules. So cis, trans, different molecules. For the 1,1, it doesn't play a role, because they are on the same atom. If you turn the whole molecule, but not here, it doesn't change. So here we have just one option, but for the 1,2, we have two options. So for the same sum formula, we have three different molecules, the 1,1 and two different 1,2. Of course, they are similar in their behavior, but not totally, because from the sum formula, same amount of atoms, it's a double bond, but the geometric form is different. So different materials, different molecules, different material, different behavior from the chemical structure. When I'd like to talk about, that's the last for now before the break, for the 1, 2, dichloroethane. Now we do not have a double bond. Ethane is the normal structure, only sp3 hybrid orbitals, only sigma bonds. So now the carbon atoms here have one bond together. The dichloro means now we have the sum formula C2 and now H4Cl2, dichloro. And the 1, 2, I'd like to talk about this one. Now we have only sp3 hybrid orbitals. And how is it looking like, the sp3 geometry? sp3 hybrid orbitals, tetrahedral. So we have a tetrahedral structure. So we have here a hydrogen. Then we have one looking into the back and one out of my plane. I tried to show that tetrahedral structure, and here we have one in the plane, and we have one out of the plane to the back. And of course, we have to talk about one is Cl. And let's talk about Cl here. And then the fourth partner from that one is looking out of the plane. So in both, you might be able to see the tetrahedral structure. We have here, it's not regular from the point how I draw it, but this here, the carbon in the middle, and we have the four partners, 1, 2, here that ClH2 is the partner, and here Cl is the partner. And we have the same here. Now the structure you might not see it as good as here, but it's a tetrahedral again. So we have two tetrahedral overlapping. Now we have all sigma and 1, 2 dichloroethane. There is no second option because we can rotate. So there is no difference. Of course, in the 1, 1 dichloroethane, then it's another one. But here we do not have these cis and trans options because we can rotate. Please keep that in mind. Here we just have one structure, only one structure. For this, here we have two for the cis and trans. Okay. Then we will have a break until something like 10 minutes to 4 and go on with the lecture in the second block. Please sit down. Please sit down and be quiet. There were some questions related to the topics we will talk about in this lecture. I will upload a table of content today or latest this week. So if you are interested in, of course, you can even try and go into the library. There are some books for chemistry, even here in Pfarrkirchen. They are all fine, and you can look it up, these different topics. They are described in different ways, but I will upload all the topics we will talk about. But of course, it's the best to come into the lecture, because here we are talking about what is relevant. In the books, you will have more background, whatever, and it's sometimes difficult to see what's really relevant for the exam. When you're here, you know exactly what's relevant for the exam. So it's recommended to join in, but of course you're free to read more about chemistry in the different books, and all of them are good in the library here. Okay, now, well, we started to talk about alkenes are different and alkanes are different. So let's start with the alkanes to do that, what we started with more systematically. Alkanes. Alkanes are hydrocarbons with no double bond. Hydrocarbons with no double bond. We already know examples. The methane molecule has no double bond. The ethane C2H6 has no double bond. Do you know the name of the C3 and H8? Propane. So that's methane. That's ethane. That's propane. What's the name of the next? Butane. So C4 and how many H? 10. So the common is the ane from alkanes, methane, ethane, propane, butane, pentane, hexane. So they are going on. The general formula is CX, when X is the number of them. How many H do we have? H 2X plus 2. Let's check for methane. C is 1, 2 times 1 plus 2 is 4, right? For 2 times 2 is 4 plus 2 is 6, right? For 3, 6 and 2, 8. 4, 8 and 2, 10. The structure is CXH2X plus 2. That's the sum formula. And they just have only sigma bonds. So always tetrahedral surrounding. Tetrahedral environment related to the carbon atoms. We saw it for the methane, and we even tried to describe it for the ethane, but it's the same for propane, butane. It's always a tetrahedral environment. Now the alkenes. Now we have the ENE minimum 1 double bond. So hydrocarbons with minimum